Hello everyone, myself Snehal Shinde, lecturer in Praveen Patil College of Diploma Engineering and Technology from Electrical Department. Subject is Utilization of Electrical Energy, subject code 22626. Unit 5, Tariff and Power Factor Improvement. So now we will see the numerical on most economic power factor. So a factory takes 200 kilowatt at 1100 volt from a three-phase supply and a power factor of 0.71 lagging. A synchronous motor is installed which takes an additional 100 kilowatt. What must be the kVA rating of this motor to raise the power factor of the system to 0.87 lagging? So the solution is factory load equal to 200 kilowatt, motor load equal to the 100 kilowatt, and total load will be the addition of it. So addition of 200 kilowatt plus 100 kilowatt equal to the 300 kilowatt. So now is the power triangle. So here is the kilowatt, here is the kVAR, here is the kVA. So cos phi 1, that is the factory load power factor, is equal to the 0.71 lagging, and by calculating the phi 1, so for calculating the phi 1 we will take the cos inverse of angle 0.7. So by taking the cos inverse of this, we get phi 1 equal to the 44 degree point 46. Then cos phi t, that is the power factor of the total system, equal to the 0.87 lagging with the synchronous motor. So phi t equal to the 29 degree point 33. So now total system power factor to be 0.87 and total load equal to the 300 kilowatt. Then kVAR load will be 310 20 degree plus 30 into 33, so 300 into 0.567 equal to 170. Then the total, the load kVAR equal to the 210 44 degree 46 dash. So 200 into 0.992 is equal to 198.4. So the power diagram is as shown in this figure. So ABC is the power triangle for synchronous motor, and OAE is the power triangle of the factory load before connecting the synchronous motor. Thus the synchronous kVAR equal to the 198.4 minus 170 equal to the 28. Therefore the synchronous motor kVA equal to the root of AB square plus BC square, 100 square plus 28.4 square equal to 104. So ABC is the power triangle for synchronous motor, and the distance from CB equal to the kVAR of the synchronous motor, and from distance D to C it is total kVAR, and it is a 300 kilowatt total. So from here 0 to E it is the 200 kilowatt load. From O to A it is kVA load. Now the angle, here angle subtended it is phi 1 and here is the angle phi t. So this is the kVA motor and 100 kV of the synchronous motor. So this is the figure, and here we calculated the synchronous motor kV. Next is the location of the power factor improvement devices for the consumer and electric supply company point of view. So the best location for the power factor correction equipment is to be installed is where the apparatus or the equipment responsible for the low power factor is operating. Synchronous condensers are used at load centers where considerable corrective kVAR is required, whereas static capacitors are used in smaller units and may be placed closer to the point where the load of inductive nature is installed. This relieves the distributors and feeders from the excessive current owing to the low power factor. In case of transmission system, this should be installed at the receiving end so that not only the generators but also the transmission lines are relieved of carrying excessive current due to the poor power factor. However, if synchronous condensers are installed near the generators, then only generators will be relieved from the excessive current component and the transmission lines will have to carry it. The scope of installing such equipment is right from generating station to the various load points. The ideal location will be that place where machine or apparatus which is responsible for the low power factor. So following are the different important locations. Load centers where considerable corrective kilovolt ampere reactive is required. Synchronous condenser as a power factor improver is used. Where a small inductive load is installed, static capacitors are installed near to. Due to the low power factor, the feeders and the distributors carry the heavy current. So the power factor improvement device safeguards in such situation. And next is the in case of the transmission line, the most suited place of installing power factor improving device, that is the synchronous condenser, is at the receiving end side of the line. This location helps the generator's transmission line are relieved from excessive current due to the poor power factor. In case of generator near to it, the power factor improvement device can be conveniently installed, but it will safeguard the generator and not the transmission line. So here we completed our fifth chapter. It was for 8 marks. So the tariff and power factor improvement. In this, we have covered tariff, what is the meaning of tariff, then desirable characteristics of the tariff. Then we have seen the types of the tariff like flat rate tariff, block rate tariff, KVA maximum demand and time of day tariff. So we have seen the different types of the tariff. Then this chapter, it consists of the tariff and power factor improvement. So our next part was the power factor. So we have seen what is power factor, that is the angle between it, the voltage and current, cos angle, cos phi. Then we have seen the disadvantages of low power factor, then advantages of the improved power factor, causes of the low power factor, and avoidance of low power factor without using power factor improvement devices. Then the power factor improvement devices using such as the static capacitor. Then we have seen the most economical method of the power factor by the formula and the derivation. Then we have seen the location of power factor improvement, then devices for consumer and electrical supply company point of view. We have seen here. So as this we have completed our chapter 5 unit, that was tariff and power factor improvement. Thank you.